are going to discuss about zero order reaction. And remember everyone, so you have to attend the evening class also. I will send the link and time in WhatsApp group. Okay. And what is the meaning of the zero order reaction? Yesterday we wrote up to where we wrote the zero order reaction.
They're independent of a concentration of reactant.
I did not get you. Where we completed? Did we complete the definition? A zero order reaction, that reaction rate independent concentration of the reactant species, right?
We
Yes or no?
completed it. Yes.
Okay. Now listen very careful. Examples of that zero order reaction. Examples: the thermal decomposition of ammonia. The thermal decomposition of ammonia. The thermal decomposition of ammonia on the surface of hot platinum catalyst in presence of platinum catalyst in presence of platinum catalyst. So that is a 2NH3 in the presence of platinum catalyst. So N2 plus 3H2. Okay, this is the zero order reaction. And next one more example: thermal decomposition of gold. What is the meaning of thermal decomposition? Thermal decomposition of gold. Thermal decomposition of gold. Thermal decomposition of hydrogen iodide. Hydrogen iodide on gold. What is the meaning of the thermal decomposition? I am asking. This we discussed in the last year. The decomposition of using heat, that is called thermal decomposition. Okay. So when the decomposition of HI and gold surface, that is an example of zero order reaction. H2 plus I2. Decomposition of N2 on hot platinum. Decomposition of N2O. Decomposition of N2O on hot platinum. Hot platinum. That means here that N2O, when the decomposition of N2O, it gives N2 plus half O2. And photochemical reactions, H2 and Cl2. Photochemical reactions. Photochemical reactions, H2 and Cl2 to form HCl. So these are the examples of zero order reaction. Now we are going to discuss about the how we can derive the zero order reaction, derivation of zero order reaction. That is nothing but rate law for zero order reaction. I am going to remove this page. Thermal decomposition of ammonia and thermal decomposition of hydrogen iodide and thermal decomposition of N2O and photochemical reaction. Okay. Concentrate here. Don't sleep. Now we are going to discuss about rate law for zero order reaction. Listen very careful here. Rate law for zero order reaction. Rate law for zero order reaction. Okay. Rate law for zero order reaction. Rate law for zero order reaction. Listen very careful, Nana. Actually, A is equal to A reactants, it gives product, whatever it is. A reactant gives product. Okay. A reactant gives product. So, how we can write this rate law? Simple. The rate is equal to minus d molar concentration of A by dt, right? So that means we can write here K, the rate constant is equal to A to the power of 0 because of this is the zero order reaction. That's why we have to represent power 0. A to the power of 0. Okay. A to the power of 0. So how we can write the rate constant? How we can write the units of this one? Units. We know already to write the units moles per liter per second, right? Mole 1 minus n minus 1, right? So moles per liter per second. Moles per liter per second. Okay. So these zero order reaction, moles per liter per second. Now I am going to write down this minus dA, molar concentration, decreasing molar concentration of A by 1 minute. Okay, Nana, listen, minus dA by dt, that is equal to K, means rate constant. This is the decreasing molar concentration of reactants. Okay, this we can write as a dA by dt, that is equal to minus K. dA by dt, that is equal to minus K. Okay, so then dA is equal to, then dA is equal to d molar concentration of A is equal to minus K dt, minus K dt. So now we have to do integration on both sides. Integration on both sides. Integration on both sides. So if you do the integration on both sides, what we will get? Integration of the molar concentration of A that is equal to minus k. This constant కాబట్టి దీనికి ఇంటిగ్రేషన్ ఉండదు. సో ఇంటిగ్రేషన్ ఆఫ్ dt. Okay. So this is the integration of dm. We are doing integration on both sides. Okay. So after this we'll get that this is integration of dA. We can write as a that is equal to minus kt plus im. Here I is nothing but constant of integration. Here I is equal to constant of integration. Constant of integration. I is equal to constant of integration. Constant of integration. Okay. So these I can be calculated by initial conditions. I can be calculated. I can be calculated by initial conditions. Initial conditions. I can be calculated by initial conditions. Okay. I can be calculated by initial conditions. That means what is the initial condition? Initial condition is nothing but when t is equal to 0, initial condition is nothing but the starting time is equal to 0, right? When t is equal to 0, then the molar concentration of A at initial time is equal to A naught. Okay, at initial time. So substitute these values in this equation. In this equation number 1. Substitute the values in equation number 1. So substituting values in equation 1. Okay, so these are instead of A, what we have to write? Instead of A is equal to A naught, right? So A naught is equal to A naught is equal to minus K into 0 plus I. Why minus K into 0? Because of their T is a temperature, the time 0, and initial concentration of A is A naught. So that's why we are taking instead of A naught and T is equal to 0. So what we will get here? Then A naught is equal to minus K into 0, K, right? A naught is equal to I. A naught is equal to I. Is it clear? So substitute these values in equation number 1. Substitute in equation number 1. So instead of A naught, I is equal to what we have to take there? I is equal to A naught, we have to take it here. So how we can write this one? The A is equal to molar concentration of A. This I am going to write here. A is equal to minus KT plus A naught, right? Why we are writing is A naught here? Why we are writing A naught? Because of their I is equal to A naught. Here I is equal to A naught. So now I am going to write here just a small correction, a small difference here. A naught minus A. A naught minus A is equal to and we can write the rate constant. This is A to the power of 0 because of this is the zero order representation of the zero order reaction. And units we know already, moles per liter per second. Minus dA by dt is equal to K is a constant. So dA by dt is equal to minus K. This minus it's coming this side K. So dA is equal to minus K dt. Now what we are doing here? We are doing integration on both sides. Integration on both sides. So dA by dt. So after integration, concentration of A is equal to minus kT by kT plus Im. There I is nothing but integrational constant. This I can be calculated by using initial conditions. Initial condition is nothing but at initial condition time is equal to 0 and molar concentration of A is equal to A naught. So substitute these values here. A instead of A we are taking A naught and minus KT times 0 plus I. So A naught is equal to I. This I value substituting in this equation number 1. So A is equal to minus KT plus A naught. So A naught minus A naught minus A is equal to KT. You have to remember these two formulas to calculation of the problems, right? So no need to remember the total derivation. So you have to remember these two formulas. Okay, did you collect the notes yesterday? You can collect the notes from Lakshmi Sai Xerox Center. And here we can write K is equal to A naught minus A by T. Yes. Now we are going to discuss about the graphs. Graph of the zero order reaction. Different graph of the zero order reaction. The first graph we are going to discuss about the molar concentration of A that is equal to minus KT plus A naught minus KT plus A naught. So that means this one. So how it will be? This graph is nothing but it will look like y is equal to mx plus c, right? Here it is a m is a k and x is d and c is a naught. Y is equal to mx plus c. So what is the slope there? There m is equal to slope. This is slope. So how we can write slope is nothing but negative. So slope etlundamma. Slope is negative. So we can draw this graph. X-axis we are taking time. X-axis we are taking time. And y-axis we are taking molar concentration of A. So this one, right? Y-axis and x-axis is a time. So this is the negative slope minus KT. So negative slope is nothing but slope is minus Km. Negative is nothing but it will come like this. Negative slope. Okay. So slope minus K. So what about the intercept, Amma? Their intercept is A naught. Intercept. Okay. Shall I remove the page? I will explain more two graphs. Or else shall I rub this side? This first page, this side. Shall I rub this side? I will explain the graph here itself. Shall I rub it? Okay, I am going to rub this side. Okay, next two graphs I am going to. So, is it clear about this graph? And one more graph. I am drawing between that A naught A naught is equal to KT plus A. KT plus A, right? So A is equal to minus KT plus A, then obviously A naught is equal to what will happen? A naught is equal to the minus KT will become plus KT, right? So here also it will be Y is equal to mx plus C only. But here is the slope is positive. The slope is positive. So here the slope is negative because of in the negative minus, right? So the here the slope is positive. So how we can take this one? Here time x-axis and a naught in y-axis. The slope is positive, amma. So like this, slope k. Okay. So here it is the intercept a. And one more graph. And one more graph. Uh, a naught minus the graph between a naught minus a, that is equal to kt. A naught minus a, that is equal to kt. From this equation we'll get this one, right? So here also this is y is equal to mx plus cm. Here c is 0. So c is 0 is nothing but, so the reaction will start from here. So the graph will start from here. So this is positive slope only because of c is 0. Here it is a time, x-axis time and y-axis a naught minus a. This is about the few graphs of the is it clear? Actually, after integration of both sides, we'll get this formula. So this is the formula of this is the formula of the derivation of zero order reaction, and this is the one also zero order reaction. This is also zero order reaction. When it comes to graph, the first equation we are taking, the molar concentration of A is equal to minus KT plus A naught. So here y is equal to mxe. There m is a slope, that is a negative slope. That's why the graph will take like this. And now here a naught is equal to kt plus a. Here it is positive slope, and here also this is positive slope. So that's why the graph will start from here. So shall I remove this? Okay. And next we are going to discuss about the half-life of zero order reaction. What is the meaning of half-life? Half-life of zero order reaction. Half-life of zero order reaction. Okay. So half-life is nothing but time in which the concentration of reactant, time in which the concentration of reactant, time in which the concentration of reactant reduced to reduced to one of reduced to one of the its initial concentration, its initial its initial concentration. Its initial concentration. So the time which the concentration of reactants reduced to 1/2 అంటే హాఫ్ రియాక్షన్ కంప్లీట్ అవడానికి ఎంత టైం తీసుకుంటుందో దట్ ఈస్ కాల్డ్ యాజ్ హాఫ్ లైఫ్ రియాక్షన్. ఓకే, so now we are going to discuss about the half life reaction. For zero odd, half life period is directly proportional to half life period is half life period is directly proportional to directly proportional to half life period is directly proportional to initial concentration of reactant. Directly proportional to initial concentration of reactant. Initial concentration of reactants and it is inversely proportional to inversely proportional to rate constant. Directly proportional to initial concentration of reactant but inversely proportional to its rate constant. Okay, so that means here how we can write that we can t half life is nothing but we can take as a t of, or we can write this is t 50%. So the time required to complete the half of the reaction of the initial concentration. Okay, so there to derivation of this t is equal to we have to take as a t of, and that a the molar concentration of a is equal to half is nothing but its initial concentration 0 a naught by 2, half we are taking, right? So the rate k is equal to a naught minus a naught by 2 by t of. Okay, so there we have to remember the t of is equal to, then t of is equal to how we can write a naught by 2k, a naught by 2k. So this is the half life period of zero order reaction. A naught is nothing but initial concentration, k is rate constant. Okay, so there t of is directly proportional to a naught. T of is directly proportional to a naught and inversely proportional to its rate constant. Is it came already? This is the rate constant inversely proportional to T of and directly proportional to A naught. Amma, here we'll get that T of is equal to, after simplifying this one only, this reaction only, A by A naught by 2 K, A naught by 2. Is it clear about this? This is the half-life period of the zero order reaction. So when comes to graph, how we can draw this graph of this one? T of time is equal to, here it is a concentration. We know already that T of is depends on concentration of the reactants, right? So the graph is increasing. Concentration increases, T of also increases. Actually, instead of T, we are taking T of amma. The molar concentration of A, actually we have to take the initial concentration. T of ante sagam kabatti, దీంట్లో initial concentration A naught by 2. Here we have to take half. K is equal to A naught minus A by T of. Okay. అమ్మ ఇక్కడ మనము ఇది ఎక్కడ వచ్చింది, ఇంతకుముందు మనం డెరివేషన్ చేసాం చూసారా, k ఈజ్ ఈక్వల్ టు ఏ నాట్ మైనస్ ఏ బై టీ, రైట్? సో ఇన్స్టెడ్ ఆఫ్ టీ వీఆర్ టేకింగ్ టీ ఆఫ్, ఇన్స్టెడ్ ఆఫ్ ఏ వీఆర్ టేకింగ్ ఏ నాట్ బై 2. దట్స్ ఇట్. ఈజ్ ఈ క్లియర్ ఎవ్రీవన్? Okay, I am going to remove this page. This is about the zero order reaction and half-life reaction. This is the formula of the half-life reaction, and this is the formula of the zero order. Zero order, and these are the graphs, and this is the half-life reaction of zero order reaction.